is that the old FEniCS that we had many years ago was getting a bit bloated and had too many extra things in it and was getting out of control. And so we decided to take a new approach where FEniCSx was going to have a tough core, which would would have all the core stuff in it, and then it would allow a whole ecosystem of people to add things on and have their own add-ons. And I think that's what Jørgen's going to talk about today, is one of the ways that you can do that.
Yes. So I'm Jørgen. You might have seen my name somewhere at some point. And I work at Simula Research Laboratory, and we're a government lab, so we are supposed to do research. I wouldn't say I do much research. I like making finite element packages, and that's not necessarily considered research, at least not by the people that give out grants. But Simula and FEniCS, that's not always been the thing. So back in 2005, Hans-Petter Langtangen went to the FEniCS meeting in Chicago, and he said that he is interested in using FEniCS as a platform for distributing the software that is made at Simula. At that time I was in primary school, so I had nothing to do with this. But I think we've succeeded quite well. So currently, packages developed partially at Simula or maintained at Simula is UFL, FFCX, dolfinx. I have my own extensions such as dolfinx-MPC. And then we have all the libraries in bold here that we're going to talk about today. There are also some libraries I promised I would talk about, but I realized I don't have enough time. So we can talk about those in breaks or over dinner. But what we will start with is SciFem, which is my playground, because it turns out not all ideas are good ideas. At least not in the beginning, because I sit down, I see a problem on this course, or I get someone dropping by my office saying, I want a solution to this, and they would like it now. And that doesn't really work when you want to have something that's going to work in the main part of FEniCS, because it might be very intrusive, it might not be well thought through, it might not even scale at first, it might not even be parallel, but you want it to be parallel and you want it to migrate into FEniCS after a while. So some examples in SciFem that has moved from SciFem now into the 0.11 release is the real function space that is now back after a 5-year hiatus. It's now back. You can use it through basic UFL real element, and you can create function spaces on it. But the design of this has gone through many iterations. It started out as an idea, and then it worked for me. But then I had to figure out a way that, can this work for everyone, and how can I get it in so that everyone else accepts it, and it doesn't become this huge bloated thing that destroys everyone's code. Another example is blocked Newton solvers. So for blocked problems, multiphysics problems, you would like to be able to specify these blocks explicitly. I do use this a lot with like the meshes of different code dimensions, and I needed a solver that could do that. But that turned into dolfinx-fempets in nonlinear problem in version 0.10. So then I can start removing these. And then the same with transfer mesh tags to submesh, a thing that I needed for some of my work. Now that's also in dolfinx. But of course, people might move slowly. So many people that have talked today and many people in my lab are still on dolfinx 0.9 or maybe even earlier versions, which means that SciFem is a place where I also try to keep backwards compatibility. So things work at least back to 0.9. If I add new features that can't be done in the older versions, I'd state that explicitly. But I try to make sure that things work for longer than the next 5 days, because things might break if you're on main. So what's next from SciFem? So one of those function spaces that I like is the function space of simple functions. And simple functions is just a sum of functions that are piecewise constant. So it's kind of a real element that's fragmented into components on your grid. So you could start by creating a mesh. You could split that mesh up into mesh tags that have unique numbers, say 4, 5, and 8. And we can now create a function space of simple functions that then only has 3 degrees of freedom. These are very convenient if you want to do material optimization, because if you have many materials, you might need 50 real spaces to describe these. It turns out that FFCX does not like having 50 different coefficients inside it, so then you need a space like this. This is something that I think should go into dolfinx. Not sure how yet. I need to figure out the correct interface, but at least now people can use it, and they can test it, and they can give feedback. So other functions, a function from this morning is the closest point projection operator. I need this for collision detections, and I think it can also be used to improve the non-matching interpolation. But I first needed to implement this and make sure it works and make it really fast. So now that I have something that works in C++, I can now slowly move it over to dolfinx now that it has a well-defined scope. Another big question is I/O. I've been working with I/O for about 6 or 7 or 8 years now. There are about 100 formats, and back in 2018, Mikhail gave a fantastic talk where he showed how we could read and write a file where you could actually look at the result and you could read it back into dolfinx. And it didn't need to be a first-order finite element space. Turns out that this is really hard because there are n+1 formats and they keep on evolving. Some of them get deprecated. They're no longer supported. They do not like any other finite elements than higher-order Lagrange elements. They do not like discontinuous finite elements whatsoever. And a few years ago, I had an idea that, okay, let's just use one format. I'm going to choose the format. It's going to be fantastic. It's going to be called adios for dolfinx. Turns out it's not the best format because, one, I got tied to adios, which I thought was a great idea at the time. I'm not that happy with it anymore because they keep on breaking stuff. Turns out HDF5 is a way more stable format for reading and writing data. But then I realized like everything I implemented in adios for dolfinx, that can work with any backend. So why do I need to tie it to adios? So then I decided IO for dolfinx. And the idea of IO for dolfinx is the realization that you should be able to use adios or HDF5 or any other backend to define how I would read and write data. If you want to use fancy function spaces, you need to use the checkpoint functionality that was already presented in adios for dolfinx. But if you're one of like 80 to 90% of the people that use FEniCS, they use P1 finite elements, then you could just use the read and write point data, which is a function that just reads and writes point data. And then you can use XDMF, VTK, HDF, or any function space that is appropriate for you. And that just hopefully makes life a bit simpler in the future. So this library has a blueprint for if you want to add a new backend, these are the functions you can choose to implement. Not every backend is going to have every function. So what I've implemented so far is a Gmesh interface, which mainly uses the dolfinx Gmesh interface, a PyVista interface, an XDMF interface, a VTK HDF5 interface, and then we have the 2 checkpointing interfaces that's just taking what was in adios 2 or in adios for dolfinx, moves that to a general purpose layout, and also an implementation with HDF5 and H5Py because it's easier to work with. But now that we've solved the I/O problem, then we can go into the more interesting and challenging mathematical problems. So imagine you have a PDE, and you have a PDE that goes over multiple spatial dimensions. So I might have a brain, and in my brain there are blood vessels, but the blood vessels are incredibly thin. And then you would like to solve a diffusion problem within your blood vessels, but also within your brain. And this is my brain. It's very square, and I have weird blood vessels. But it turns out the mathematical formulations for these can be written with non-local operators, which is this capital Pi R and capital Pi here, where you can have averages, where you reduce your model from a 3D model to 1D model, and then you're going to compute integrals surrounding your 1D networks. But of course, since this grid doesn't align with my, my cubic brain, it means that I need to do some non-matching interpolation to get this to work, and I need some non-local operators. So how can I do this? I can do this by using an idea that Miroslav Kucha at Simula started with in like 2018 or so, and he implemented in legacy FEniCS called FEniCSxii, where you want to make these kind of restriction operators that are non-local, where you can give a radius to your circle or your disk that you want to average over, or if you just want a single trace, you give a radius and you can give a degree or a function space. And now you want to create averages in UFL. So you want to say, I want to average over this circle, or want to average over this disk. So what I've done is I've moved this into dolfinx and also made sure it works in parallel, because what's the point of moving it to dolfinx if it doesn't run in parallel? Then you could just run old FEniCS. And then you can write these operators directly inside UFL. You get these, here we have a 1D measure where you have the average of U on the 1D line, and you also have a similar operation down here that couples these 2 problems. And now you can send those into my custom assemblers. Like I need custom assemblers for this because I need to make some intermediate parallel interpolation matrices. You can pass them in and you can solve this problem, and they're also available online. So there are a lot of QR codes in this, but the slide deck is on my webpage, so then you can use that to get to all the different implementations. But this is things that have been developed over a long time, but it needs to mature and figure out how can we do these things in parallel. And since we already saw that my brain is very simple, it only has one blood vessel and it curves, but what if my blood vessel starts bifurcating like this? Then I need to do something. I need to be able to solve problems on these kind of graph structures. It turns out doing that in parallel is not that easy. But thankfully, Andreas Sillian invited me last year to Luxembourg where I could sit down with Paul and we could chat about this. And we were able to implement a way of doing this properly in dolfinx. So there is a new parameter in dolfinx called max facet to cell links, which you need to give, and then you can have as many connections between facets and cells that you would like, which is very much required to do something properly, because what would happen in FEniCS prior to 0.11 is that it would, or 0.10, it would run, but it would give you disconnected grids, and it wouldn't tell you anything, it would just do that, and then you would be left with a weird result. So that's now been fixed, but with this, I can also then start working on graph-based, like combining networksfenicsx and FEniCSx, which is something Ingeborg Gjerde that was at Simula did back in 2022, but now in FEniCSx and also with MPI, because I want to solve this on massive structures like the blood vessels in my brain when my brain develops a bit more. But something that really was clear from the previous FEniCS conference is that people are missing dolfinx-adjoint. So I spent a few days last year starting with this, but I didn't give it a name because I'm not proud of the implementation. I'm still not proud of the implementation. But there is at least now a prototype of dolfinx-adjoint where you can do linear and nonlinear problems with function control or constant control. And the difference between dolfinx-adjoint and dolfinx-adjoint is you're going to be more explicit than, like, that's the whole game of dolfinx. We want to be explicit with what we're using. So the key things you need to use is you need to use the dolfinx-adjoint function, because I need to be able to track this so I can differentiate through it, and you need to use the dolfinx-adjoint linear problem or nonlinear problem. But this then works with pi-adjoint, which was the backend of dolfinx-adjoint, and then creates your, you can create your assemble scalar, you can create your control, you can do your reduced functional, and you can do optimizations, for instance, through Mula if you want to avoid mesh dependency. So it exists. It's not perfect. There are many things I need to fix, including things that Henrik needs for his complicated biomedical problems. But it's at least a start. And if people start using it, then I might get some feedback and I can figure out the right design, because I'm not happy with how it looks under the hood. It looks okay on the surface, but it's not pretty. So I would like to make this better and especially make it really good for time-dependent problems. So if you have some good time-dependent control problems, please give them to me so I can figure out how to do this in a better way. Finally, something that came to fruition because I met with Rob Kirby last year is one usually wants to do time derivatives, and we usually do backward Euler, forward Euler, or Crank-Nicholson. But if you want to do higher order time derivatives, you would need to write them all out in, say, a Runge-Kutta scheme, and that's quite tedious. So what you want to do instead is to use ERCSUM, which Rob Kirby made for Friedrich, to do time derivatives with higher order Runge-Kutta schemes. Now you can do this with dolfinx as well as of Sunday. So you can now use the capital DT of U operator that is in ERCSUM. You can then get your time derivative. You need some special boundary conditions from ERCSUM, because I think this is the right way of doing boundary conditions, but it's something I need to discuss with developers on how we can get into dolfinx. But then you can use this time steppers from ERCSUM. So if you want a scheme that's 6th order accurate, you just take the form that we had that didn't say anything about how you would do time. It just says time derivative. You say how many stages you want. You get a 2 times number of stages accurate scheme, and you can solve this problem. And this now works with dolfinx. It doesn't have all the features that ERCSUM offers. That's going to happen over time, but it's a start. And we need to start somewhere and get people to use it. Of course, I don't do all of these things by myself. I work with many, many people. We have Henrik and Marie at Simula. We have Ashan, Rob, Pablo that works on the ERCSUM bit. We have Cecile, Paul, and Joe that I worked a lot with network problems and also submesh problems with. And Matteo, I promised I would talk about how to integrate FEniCSx with Jax, but I realized I don't have time. So there's a QR code. You can also come and talk to me. We have some ideas of how to do this nicely now. And we think that we should implement this inside dolfinx-adjoint as well, so things become properly differentiable. There's going to be a FEniCS workshop in the fall. I'm just going to leave this here. You can scan this and look at it or just talk to me. We have 20 invited speakers. There's going to be a Zoom link that's going to be public You just need to register so you don't get flooded by spammers. Or you can show up in person if you would like to, but then you need to fill in a sign-up form that's soon gonna arrive. Probably went way over time. Sorry.
No, just about on time, but not much time for questions.
Yeah,
anyway,
that's fine.
thanks, Jørgen.